Well, what exactly are those little particles? We call these subatomic particles because they're particles that are smaller than atoms. So there's three we need to know about: protons, neutrons, and electrons. So protons and neutrons have very similar masses. For our purposes, they're the same. Electrons have essentially no mass, almost negligible. So if we look at the masses in kilograms, protons and neutrons, about 1.67 times 10 to the minus 27. So that's a decimal point, 26 zeros, 167262 kilograms. It's really, really small. So this number is just hard to even look at, 10 to the minus 27. So kilogram is obviously not a great unit for measuring the mass of a proton. So let's use a different unit. There isn't, well, maybe there is one, but I am not aware of a metric unit that gives us an exponent of minus 27. What I know goes up to about minus 12 or minus 15. So they came up with a new unit. And so it sounds a little flip to say, oh, well, we made up a unit. Where did all units come from? Somebody made them up, right? All units are made up. So it's okay for scientists to make up a unit. So they made up a unit in a way that would be very useful. It's got a super creative name, atomic mass unit. It's useful for measuring the mass of atoms. It's a unit to measure atomic mass. The way it's defined seems a little bit crazy, but they did it in a way to be convenient. One atomic mass unit is 1/12 the mass of a carbon atom with 6 protons and 6 neutrons. What that ends up meaning is that a proton and a neutron each have an atomic mass of about 1, really close to 1. For our purposes, it's 1. The electron is much smaller than the protons and neutrons, and so its mass, even in atomic mass units, is small, 0.00055. Essentially 0. Most of the time, the mass of the electron doesn't matter at all. So I want you to know, in atomic mass units, the masses of these particles. So proton is 1, neutron is 1, and an electron is essentially 0. Okay, so you should know that. And then charges. These are relative charges. They can be measured in actual charge units like coulombs, but it doesn't really matter for our purposes. So a proton has a +1 charge, a neutron is 0, and an electron has a -1 charge. So you need to know these, and of course, the names of those guys. Okay. Proton is positive, neutron is neutral, electron's negative. Question?
Now, as far as calculations, would we use the 1 or would we use the 1.0073 when we're calculating?
That's a good question. So if you're calculating, are you going to use the 1 or the 1.0073? Mostly, we're just going to use the 1. There may be homework problems or something where you might even have to use the mass in kilograms. You look it up, you definitely don't remember that. I do not remember the decimals on these. The difference here is in the 4th significant figure, and so unless you're doing incredibly precise work, it really doesn't matter. So approximately 1 is good enough to remember. Just to give you an idea of the size, relative size of protons and electrons. So if the proton was the size and mass of a baseball, the electron would be roughly the size and mass of a grain of rice. Okay? So very small in comparison to this. The proton is nearly 2,000 times as heavy, as massive, as the electron. So most of the time when we're thinking about it, we can just say, well, the mass of that electron doesn't really matter. So matter is mostly empty space, and yet it sure seems solid, right? You crash into something in your car, and yeah, you have a hard time convincing anybody that you just crashed into empty space. Why does it appear solid? It's because the variation in density between the nuclei and that empty space around it, that variation is on a scale that is so small that we can't distinguish it. So it's a little bit like looking at a large scaffolding, or this looks more like monkey bars to me, the old-fashioned metal monkey bars that we used to kill ourselves on when I was a child. So if you go in and look at this closely, you see that there's these metal bars, but most of this structure is empty space, right? But if you had a scaffolding like this that was like 10 feet tall and 10 feet wide in the center of a football field, and you rose up in a blimp or something or an airplane above it and looked down on it, you get some distance from it and it begins to look solid, right? Because as you get farther away, the difference between the bars and the empty spaces becomes less obvious. So because all of this with the protons and the empty space around the nucleus is on a scale that's so tiny, when we look at matter, we see solid. Any questions about that? So electrical charge is very important in understanding how matter behaves. Electrical charge is a fundamental property of protons and electrons. The protons have a positive charge, the electrons have a negative charge. What's important to understand about a charge is electrical charges behave a lot like magnetic fields do. So we've all probably played with magnets, or at least used a magnet to stick something on the refrigerator, right? Magnets have a north pole and a south pole. One end is different than the other. And if you try to put two north poles together, they repel each other. If you try to put two south poles together, they repel each other. But if you put a north pole to a south pole, they are drawn to each other very strongly and they click together, right? So in a magnet, the same pole will repel and opposite poles attract. With charges, opposite charges attract each other, like charges repel each other. Two positive charges will repel just like the magnets, and two negative charges will repel. And these have equal magnitude, so a positive charge and a negative charge. When you put those two together, they're going to be attracted to each other, but then overall, their charges add up to 0, and so they neutralize each other. Any questions about that?